do, so maybe it's a good time to start. It's a pleasure today here to have this young Yang. He's a postdoc of Lei Ying at our own University of Michigan. Here, today he's talking about online learning in queuing system, and it's a pleasure to have you here. Thank you for giving the seminar.
Thank you for the introduction. Thanks for inviting me to this conference, seminar. Today I will talk about online learning in queuing systems. Queuing system is motivated by many real-world examples. It's a fundamental framework for modeling many applications like ride-hailing, where the riders and drivers, both riders and drivers, form queues. And in organ donation, like this patients forming queues and also the donors. And in crowdsourcing platform, the jobs are submitted by users and they wait for be served by workers. And also in cloud computing, the jobs are submitted by users to the cloud, and they're waiting for this to be served by virtual machines on the cloud. Like in many applications, the system primitives are unknown, and but we can observe data. So to optimize the performance in these systems, this like motivates us to use learning and decision making to optimize the performance in these systems. The conventional approach of doing this is predict then optimize. It works like this. First, we collect data using some policy. We collect a lot of data, and then we learn a model from this data. And then we optimize based on this learned model and make decisions. But there's some drawbacks of this approach. Like first, the cost in the data collection phase, the policy we use is usually not optimal. It's usually even not good, because we would like to explore different settings, different regions of the system. So the policy will induce a large cost in this phase. Also, the model, like if the system change over time, we need to relearn the model because like original model changes. The original parameters or primitives is not good enough. It's not good anymore after the environment change. So we focus on the second line of approaches. We do online learning and decision making simultaneously. Like one example of this approach is we first learn a model, then we use the model to make decisions, and then we get some new samples, and we will update our model based on these new samples, and we repeat this process. The challenge is, how do we design algorithms with theoretical guarantees in queuing system, like in the second line of approaches? I will talk about two of my works here, but I will focus on the first one. Mainly focus on the first one, which is learning-based pricing and matching in two-sided markets. This work is motivated by two-sided markets, like as I mentioned in ride-hailing, one side is rider, the other side is drivers. And also in meal grocery delivery platform, one side is customer and the other side is shoppers or drivers. And also like in organ donation and crowdsourcing platforms. The model we are considering is a system of two-sided queues. Like there is a bibyte graph, but it's not necessarily complete. Like there are some links that is incompatible. You can only match the customer and server only if it's compatible. So only if there's a link there. Let's take a ride-hailing platform as an example. On one side, it's the customer side is rider and the server side the driver. Like we consider a discrete time system. At each time slot, the platform the platform set a price for each individual queue according to the pricing policy. Like the prices are different for different queues. And the according to some demand or supply function, the arrival rate will be determined by this price. Like on the customer side, the price according to the demand function, like the curve there, if the price increase, then there will be less customers willing to join the queue. So the arrival rate will be smaller. So it's like a decreasing function. On the supply side, like if the price the platform pay the drivers is higher, then the drivers will be more willing to join the system. So the arrival rate will be higher. We assume that arrival is Bernoulli. And then the arrivals are realized based on this arrival rates. And then the platform implement a matching policy. The match paired will leave the system immediately. And then we go to the next time slot and repeat this process. There's another equivalent model for arrivals, which is more reasonable and practical. After we set the price, after the platform sets the price, there's for example, on the customer side, for each customer, there's a value that the customer thinks the trip, like take ride-hailing the system as an example, the passenger will think the value of the trip is V I of T. It's drawn from an unknown distribution Fi. And if the price is higher than their value, then the customer will just reject the price and leave the system. Otherwise, they will enter the system if they accept the price, if the price is less than their value. And on the server side, it's just the opposite. Like if the price is higher than the cost of the driver, then the driver will accept the price and enter the queue. The cost of the driver is like the fuel cost and opportunity cost. But it is easy to verify that this model is actually equivalent to the model we just described, like using a demand and supply function. So we just focus in the following, we just use the previous model for simplicity.
So this queuing, like customers can accumulate.
Yeah, it's queuing. Yeah, they can accumulate. Like there could be more than one in each queue.
The customers are not sensitive to the
No, we just
abandon or
no, we don't consider abandonment, but it's an interesting direction. Yeah.
So they stay in the system.
So
customers stay in the system.
Yes.
They're concerned about the
we want them
stability or
like no, because we want to minimize the queue length. We have two objectives. One is the profit of the platform, and the other is the queue length of the system. Yeah. So yes.
What guarantees stability?
There's not not necessary. Because like you think if it is a one link system, there's only two queues and one link. If the rivals and the rivals are the same, it's a critical point. So the is a symmetric random walk, then the queue length will go to infinity. So for two-sided queue, it's more difficult to get stability result.
But that's not something you care about. Yeah?
I no.
Oh,
I care about the queue length. That is the waiting time, equivalent to the waiting time of the customer and the drivers. Yeah, thank you. So we consider two objectives. One is the profit. We consider finite time horizon to time t, capital T, and the profit, the sum of the expected profit. And the profit at each time slot is the revenue minus the cost. The revenue is the sum over all Q's I, and the multiplication of arrival rate along the I of t, and the price of the at that time slot for the Q. It's basically the average revenue that coming from the passengers. And the cost is similar. It's just sum over all drivers, like sum over all driver queues, and the arrival rate times the price.
Every customer is guaranteed to be serviced eventually.
No,
That's
but
why we extract this price from them.
no, we assume they whenever they enter the system,
They pay the price.
Yes.
So they may never leave the system.
right. It's somehow not that realistic. But yeah, but if we can control the queue length, we can get a bound for the profit if we assume they match. The platform get a profit after they match. Yeah. Yeah, if the queue length is finite, then it's fine. But yeah, but we have some. You can see later we have some guarantee for the queue length. So we assume that the demand functions and supply functions are monotone, as I mentioned. And the second objective is we want to minimize the average queue length or average over the whole time horizon, average over the time horizon, the total queue length at each time t. The question is, if the demand and supply functions are unknown, how should the platform do pricing and matching? Let's note that what we can observe is actual arrivals at each time slot and the prices we set, prices the platform set. But we want to learn online to maximize the profit and minimize the queue length. At this point, any questions for the model?
So the queue line is not visible to customers and the servers, right? Or
it's a bit not visible to the customer and server, and yeah,
in other words,
not visible.
it does not contribute to their decision.
It's not strategic. They're only sensitive to price.
Right.
In an aggregate sense.
Yes, yeah, right.
But it is visible for the service operator, the freelance.
Service of what?
The person who make the decision to set the price. Is that they know each freelance.
You're saying
The system manager.
Yeah, the manager, yeah.
Observe the state of the system, like, right?
yeah, system can see the same, yeah, but the customers just make decision according to the price and their own value and their own thinking of the trip. Yeah, thank you for the questions. So there are some related work. There are many works about matching pricing and for two-sided queues. But most of them assume that the demand and supply functions are known by the platform. And there's also a line of work like used on online learning in queuing. where they learn the system models online. But most works focus on one-sided queue for learning. Here we study two-sided queues. And some of works just learn a static pricing policy. We focus on dynamic pricing policy, which means like the platform can decide the price according to the state of the system, according to the queue length. Like because it's an online learning, we want to define a regret and a baseline. First a baseline and then a regret. Baseline we are considering as a fluid baseline proposed by WAMA 2023. It is an optimization problem. We maximize the profit function, assuming the demand function and supply functions are known. Like if the functions are known, then we can also write the profit in terms of the arrival rates, because the arrival rate is one-to-one function of price, and objective is we assume that the objective is a concave function of the arrival rate. It's reasonable because like in economy, like they have the more you it's like diminishing marginal return. The more you invest, like the less increase of the marginal return. And the constraint here is just a flow balance equation. It means that the arrivals is equal to the matching rate, which is also equal to the arrivals on the server side. This makes sense because like if you don't satisfy this constraint, then the queue length will increase linearly. Like if you think of a unlinked system, if the service rate is greater than the arrival rate, then like not service rate, sorry. It's if you look at a two-sided queue one-link system, if the arrival rates are not equal, then one of the queues will like increase linearly in time. Yeah, we can prove that. We prove that the optimal solution to this optimization problem is an asymptotic upper bound under any stable policy. Here, stable, I mean some rate, like mean rate stable is like it's sublinear in T. It's not the true stable that the queue length is finite, but its queue length is sublinear in time. So the regret is defined as the T times the optimal solution, optimal value, minus the sum of the profits, the actual profits. And then the objective becomes minimize the expected queue length and minimize the queue length. We want to find some trade-off between them. It's like intuitively this trade-off. Let's think about it intuitively. Like if we reject all arrivals, then the queue length will be 0. But the regret will be order T, because you reject any arrivals, you don't have any revenue. Second case is if we follow the fluid solution. I mean, if we know the demand and supply function, and if we know the fluid solution, we just follow exactly the fluid solution, which is lambda star mu star. If you look at the single link system, the queue length will increase in order square root of T, because it's a symmetric random walk. And the regret will be 0 because you follow exactly the baseline we are considering. So if you look at this figure, like the red points are what we just talked about, and we prove that a low bound, that the red area here is impossible. That is, there's no algorithm that can achieve the trade-off in the red area. Like it means if we want the average Q length to be smaller than t to the gamma over 2, regret at least will be t to the power 1 minus gamma.
Where is that coming from? That constraint on average Q. Why do you care about? I thought you didn't care about Q. Just cared about maximizing profit.
I care about Q length, but like, I'm sorry, maybe I'm misunderstanding. Like, I care about Q length, but I cannot prove the Q length is stable. I care about the Q length, but like the Q length will increase in T.
It will grow unbounded
Yes,
in T,
yes,
but you have like a time dependent
yes,
requirement.
yes. Sorry.
And trying to achieve the pricing.
Uh,
Like the pricing scheme that guarantees that maximize profit subject to that kind of constraint. Is that the?
That is a lower bound result. We haven't talked about the pricing algorithm, pricing scheme. Like it's like for any policy. If the policy, if the Q length of the policy is less than that, then the regret is at least that. Yeah. So the question is, can we achieve the trade-off in other areas, especially the line, the boundary of this impossible regime? Yeah, under some assumptions, well, we can have some results. We assume that the demand and supply function and their inverse function are Lipschitz smooth and non-zero derivatives. And we also assume that the initial set of arrival rates and prices are nearly balanced, which means that we know a set of prices at the beginning of the algorithm that the corresponding arrival rates is approximately satisfy the flow balance equation. But there can be some error, but we allow some error there. I just talk about it like intuitively because it's technical. I don't put the formula here. The third assumption is something like something weaker than a strong convexity. And the result is like this. Regret under some algorithm we proposed. I will talk about algorithm later. The regret is order t to the power 1 minus gamma, and the average Q length is t to the power gamma over 2. In the figure, it's like the green area is achievable by our algorithm, and particularly the line, the boundary there is also achievable. Next, I will talk about the pricing algorithm we use, algorithms we use, and the limitation of the result. Any questions? Yeah.
Is there any correlation between the Lipschitz constant L and that like lower bound coefficient you have? I don't like recalculate.
The V there?
Yeah, is there any correlation between that and the L Lipschitz coefficient there? Are they kind of related? It's more smooth. Is that a better bound or no?
I make the assumption separately, but No, I think the last assumption is something like strong convexity. It's like the it's like you think of a quadratic function. The v is something like the curvature of the function. Yeah, and but the Lipschitz is just some more like smoothness, right? Not smoothness, but like a change of the function value. Any other questions? Okay, before I talk about algorithms, I will first talk about the challenges in this problem. First, the first intuitive algorithm is like you can explore then commit. That is you can discretize the price space, and you like try different prices, and you see you can estimate the demand and supply function approximately after you tried many prices, and then you optimize based on the estimated functions. But this is not optimal, because when you try the prices, it's hard to control the queue length. Like when you like explore. And second idea is a Montian bandit. You can like again discretize the price space and then do Montian bandit. View each price as an arm. But again, it's hard to control the queue length. And reinforcement learning algorithm work, like especially deep reinforcement learning, but like it does not have any theoretical guarantee, because the state space is infinite for queuing system. And yeah, and I don't know, I'm not aware of any theoretical guarantee for that, for deep reinforcement learning. Like the key challenge, one of the key challenges is the indirect control challenge. It means that we don't control the arrival rates. This optimization problem is our baseline, but it's in terms of the arrival rates, lambda, mu, and x. X is a matching rate of each link. It's if you remember, it's the average matching rate of each link. But like we don't control this arrival rate and matching rate. We can only control the prices. But the problem is non-concave in terms of the prices, because the constraint is linear in terms of the arrival rate, but it's because the demand function and supply function are non-linear, so it's non-linear in terms of prices. So the whole problem becomes non-concave. Now, even worse, the constraint set is actually unknown, because we don't know the demand and supply functions. So if we view the constraint set is unknown in prices, but it's known in the arrival rates. The second challenge is careful learning. We call it careful learning. It means that we, in a learning process, we want to also ensure small queue length in the process. You need to control the queue length at the same time while we are learning, getting samples.
So a very high price will cut off demand, no?
Yeah, that's one of the policy to call the threshold policy. Performance is not optimal. Let's think about that. If you don't satisfy the constraint, like you can think of a simple example like one link system, where like lambda is greater than mu, then even you put a threshold there, the number of times you violate the threshold, you cut the arrival, it's square root of t, right? I'm not sure, but the point is like whenever you use the threshold, you have some regret, like profit regret, because you satisfy the profit for that threshold. Yeah. Thank you for the question. And the third challenge is manage the trade-off between the regret and QA. If we first talk about our matching algorithm, the matching algorithm is from the previous paper from previous literature. It's the longest queue first algorithm, which is also equivalent to a Maxwell algorithm. We iterate over all the queues. First, let's take a look at, let's match the customer at the first queue. It just match them with the longest queue on the other side. Here is just match the server Q1, right? It's just two drivers there. Yeah, and then we go to the next queue, customer Q2, and it's empty, but so we go to the customer Q3, then they match the longest queue on the other side, but if they're equal, if the number of drivers are equal, then you just break the tie arbitrarily. Let's say we do this. And then we go to the server side and do the same thing. The innovation is our pricing algorithm. We combine zero order gradient ascent and bisection. We call it zero graph. Like first we have some.
Here
Yes.
the prices don't matter. Like when you do the matching, you're not aware of like the rewards that you get when you match a pair.
No, because we assume we already get the revenue after they enter the queue.
If you already captured that.
Yeah.
Pair.
Yeah.
I see.
Yeah.
There's a little cheating.
Yeah, that makes it easier. Yeah. Yeah, we consider matching and pricing separately.
Yeah.
Thank you. Yeah, the initial point X, we have some initial X, record that X is the matching rate. Yeah, but we cannot control the matching rate, but we just start with some matching rate. We randomly perturb the point in a random direction and the opposite direction. For each point, we want to find the price that corresponding to that point, that arrival rate, using bisection. Assuming we have some initial searching, like in this figure, the target, it means one of the point, one of the rivalry. And we have some price searching interval at the beginning. Then we first calculate the midpoint of the interval, set the price, and run the system with that price for a number of times, like let's say n times. Then we get NIID samples of the arrival rate. And we take a simple average, we get an estimate of the arrival rate. Let's say the estimate is in the figure there. And then we compare the estimate with the target arrival rate. We update our search interval. And it's just a bisection, but with the samples and taking average to estimate the function value. Like after we done the bisection for this step, we get an estimate of the profit for each point. Then we can calculate the gradient, estimate the gradient using the profit of these 2 points. Let's say the profit 1 is greater than profit 2, then the gradient should be like in this direction. Then we just do the gradient ascent. And we repeat this process. This actually solves not solved, but address the indirect control. challenge we just mentioned. We optimize in terms of the arrival rate, but we control the prices using bisection to match the arrival rate. And like here, we haven't talked about how to control the queue length. So assume the zero grad algorithm produce a price P. Like know that the price P will converge to the optimal price P star. Like a simple idea is that you can just use a price P, but this is not good because even if you can already converge to the P star, the price P star, like it still has a large queue length because even if the arrival rates are equal, the system will be in a critical point, so the queue length will increase in square root of t. So there's a two-price policy proposed by WAMA 2023, but they assume the demand function and supply functions are known. We borrow their idea. If we borrow their idea, let's say if the queue length is less than a threshold tau, we keep the original price. But if the queue length is greater than the threshold tau, we just increase the price. For the customer side, we increase the price such that the arrival rate will decrease. This will give us a negative drift of the queue length, so that we can control the average queue length. But the thing is, like, when we increase the price by alpha, we have bias samples for our bisection. Like if we implement a P plus alpha price, then the arrival samples we get is different from the original P. So we don't have a good learning. So we propose a probabilistic two-price policy, where we just in the case where the queue length is greater than the threshold, we just like randomly choose either the original price P, or we increase the price by 2 alpha with probability half. In this way, we can at the same time we adjust the price with a constant probability, so we maintain a negative drift at all times. But at the same time, we also get unbiased samples P, like set P here, so it ensures fast learning.
I have a question.
Yeah.
Is there anything special about probability 1/2 there? Because you're not.
No, you can use any constant. Yeah.
So the 2 alpha and the probability of 1/2 have to balance out, right? You want an expectation with alpha there, is that right?
Yes.
Okay.
Yes. Yeah.
You do this to just have more samples. This is all about number of samples, or
Yes, I have more samples. Yes, but in the original two-price policy, we cannot have some lower bound for the useful samples. Like basically, you need to prove that the number of time slot that the queue length is smaller than the threshold is at least good enough, like linear in T. But like it's hard to get that result, and I'm not sure that is even true or not.
I have a follow-up question on that previous question. So, okay, so if you can choose any probability of 1 between 0 and 1,
Yeah.
and you always have fast learning with negative drift at all times, why not choose a probability that's as close to 1 as possible? Why choose 1/2?
Oh, yeah.
0.999.
Yeah, it's just a constant, like multiplicity constant at the grad, right? You choose a very high.
I would assume there's an optimal somewhere, right? There's an optimal way to get as much of the first approach as you want, as you can, while still having the property of the second approach, right? In other words, the advantage of your second approach is negative drift at all times, and that's true irrespective of that probability.
Yeah, it's true, like for any,
Any probability is
Probability.
not exactly one. Anything
Right.
else.
right, but the thing is you, kind of like, let me think about that, if you adjust like, if like this probability is, almost one, then this alpha should be very large. And not, right, in order to, but like this will have some profit regret. When you adjust the price, you deviate from the original optimal price.
Okay, all right, I see.
Yeah.
Thank you.
It's just a trade-off between regret and Q length. Yeah, yeah, good question, thank you. So the careful learning challenge is suggested here. So this is related to your question, like we need to adjust the alpha, choose the alpha and other parameters to carefully balance the Q length and profit regret. So summary of our pricing algorithm, we combine the gradient ascent and bisection, and we use a probabilistic two-price policy to control the Q length, and we choose a parameter carefully. And the limitation is we are not sure whether the other areas is achievable by any algorithm or not. But we have some conjectures, like the yellow area here, like the yellow area here is probably impossible because it requires regret to be less than square root of t, and also require the Q length to be small, smaller than square root of t. The conjecture is based on like the banded convex optimization that they have a lower bound in the literature saying that the regret is at least square root of t. Yeah, but we are working on this. And the white area is an unknown and open question because it is difficult because of the indirect control challenge. And we are not sure if we can have a better algorithm today. So I will talk about analysis and any questions so far?
So you have your trade-off between average Q length and expected regret. You have, I would assume you'd like to be on the Pareto curve somewhere, right?
What curve?
For a specific amount of regret, you want the lowest Q length.
Yes. Right.
So you have a green region here that's achievable, and you can go down to the bottom of that.
Yeah, the line. Yeah.
But then you're on the boundary of impossibility. So does something, is there a reason not to be on that boundary? Is there some sort of singularity or something that happens in your implementation if you're exactly on the Pareto front?
No, you can always actually you can always set on the boundary, like set the thing on.
So the boundary, it includes a boundary. You can't just,
Yes.
it's not just getting close to it, but you can actually do feasible.
Yes, it includes that. Yes, it includes that boundary. Yes. Okay. The analysis is basically based on the Lyapunov method and two-point method in zero-order optimization. There's a few challenges. I won't talk about the whole proof or the workflow of the proof, but I will talk about some challenges we encountered and how we solve them. The first one is we think we need to condition on the concentration of the rival samples for all iterations. It's this event is defined as like the average of the arrival A. A is the Bernoulli random variable. The distance between the average of the arrivals and the arrival rate lambda of L. M is the bisection iteration L. It's smaller, it's small for all iterations. This is the difficulty is that this event is correlated with the randomness in a two-point method. If you remember that we first perturb the point in the direction and opposite direction in the algorithm, that randomness is correlated with this event because the 2 point will affect the price and arrival rate, which will affect the arrival samples. The idea we use is we just assume this event, we define a new event, it's not the same event, that it holds for any lambda, it holds for any arrival rate. So it becomes uncorrelated because we define the event for any arrival rate and any price. And then because the arrival rate is continuous between 0 and 1, so we use covering argument to bound the probability that this event does not hold. And the concentration inequality. The second challenge is we need to bound the number of useless samples. By useless sample, I mean the samples when we adjust the price to control the Q length, those samples is biased. We don't use those samples. So we need to bound the number of those samples. The way we use is just, if you think about it, this is just a starting time, right? Before obtaining the n useful samples, what's number of useless samples you have? It's not difficult. It's like you just use Walsh lemma, you can bound them. Another thing is we need to bound the regret induced by that adjustment, by this adjustment. But the intuitive way to think about that is if you have a function like profit function f p plus alpha, you adjust the p by alpha. You can do a Taylor expansion, then you get fp plus a first order term and a second order term. First order term is 0 if p is optimal. Like if the optimal point is stationary point. And so intuitively the order should be t times alpha squared, the regret. Yeah, but like in our problem, it's not as easy as this, like because the optimal point is not necessarily the stationary point, it could be on the boundary. And also the f is not convex. I mean, in terms of p, f is not convex, it's in terms of arrival rate is convex, concave, sorry. So we just use KKT conditions on the arrival rate region and arrival rate in terms of arrival rate, and then we use some Lyapunov method to bound that. I will just skip the details, but intuition is clear. Here are some results, numerical results. We use the New York City ride-hailing trips data. The profit, the left-hand side figure is a profit. And the blue line static policy means we, first, all of these policies we are comparing use our learning algorithm, use our pricing algorithm, but the static policy just don't use the probabilistic two-price policy to control the Q length. It just use the zero order bisection, but don't care about the Q length. you can see that on the right-hand side, the blue line is Q-length is increasing fast. And like the threshold policy means you use a cut threshold to cut off the Q-length. Like I mean, when the Q-length is greater than the threshold, we just reject all arrivals. It works, but the average Q-length is like larger than our algorithm, which is the green line. By the way, in order to compare it fairly, we use the parameters such that all the three policies have same order of profit. So the profit curve looks like almost the same. Yeah. And we also like combine the objective together. We consider, because the Q-length is approximately proportional to the waiting time. We set the holding cost 0.5. It's like the dollars you pay the customer and drivers per unit time they're waiting, per unit waiting time. You can see the probabilistic two-point policy is like significantly better than the threshold policy. Okay, any questions? I think I don't have time to talk about the second work.
On slide 26, are you choosing the grid's 3 powers of 2 with the bisection being ln of 2 convergence rate, or not related at all?
No, I just want to set a log, but like 2 is somehow looks nice. It is, yeah, I want to like talk log proc, because the Q-length and the profit is like t to some power, right? If I put proc a log, then it becomes linear. Yeah. Maybe I briefly talk about the second one. It's just multi-server systems, learning and scheduling in multi-server systems. Skip the motivation. The model is like the multiple job types, and each job type form a queue. And on the right-hand side are multiple servers, and the servers are heterogeneous. And there's the arrivals along the 1T, 2T. And at each time slot, we consider discrete time system. At each time slot, there's arrival coming. And according to some scheduling algorithm, we route the jobs to the servers. And then for each server, we have some service time, like service rate, average service, which is the reciprocal of the average service time. We assume that we consider heterogeneous servers, and we consider different job types. For different job type and different server, we have different service rate. Right? We denote it as mu ij of t for job type I and server j. And then there's a well-known algorithm called Maxway, which you just schedule the queue that has the maximum product of the queue length and the service rate. But the Maxway algorithm usually assumes that we know the service rate mu ij of t. But problem is if we don't know the arrival, we don't know the service rate, and also the service rate is time varying, what should we do? And it's a very intuitive algorithm, and also we use is that we use a Bandy algorithm, like UCB, upper confidence bound algorithm, and combine it with Maxway. The algorithm we use here is like we make a weighted average of the service time. We focus more on recent samples and less on past samples. And then we subtract a bonus term like in UCB algorithm. So the whole term becomes an upper confidence bound on the true service rate. And then for each available server J, we'll schedule the queue that maximize the product of the queue length and the estimated service rate. You just substitute the UCB estimate into the Maxwell algorithm. And we have shown that the average queue length is order 1 over delta, where delta is the traffic slackness, which is the in a single queue, like it's just mu minus lambda, is service rate minus arrival rate. And this order is optimal because for MM1 queue, 001 queue, the order are the same. We also have a many time bound and some guarantee for the non-stationarity. Yeah, that's all I want to talk about today. Yeah, thank you. Yeah.
Any more questions? Okay. We had a lot of questions also during the talk. Is there anything on the chat maybe?
No, what?
It's Jan, is there anything on the chat or YouTube maybe?
Oh,
Maybe. Okay, so thank you so much again.
yeah, thank you. Thank you.
Plans for everything. We're free the